All right, good morning. So we'll start the second lecture for today. Um, just very quickly, before I start, I published the Canvas course. Everyone should have access to it, all three sections. Two of the sections I combined. So essentially 4803 and 8803 in-person lectures. You are going to see this exact thing here. Um, Piazza is something that we all need to use. So let me see if I can go here just to see if it's working now. Yes, perfect. Okay, so you should be able to access Piazza via Canvas itself, or you can do an app on your phone, and you should be able to access from there or on the website as well. It should be fine. So please go ahead, and if you have any kind of logistical or technical questions, this is the best place to ask. Um, Regarding the office hours, so I'll have my office hours for about 2 hours in Centergy, but I'll also have a Zoom link available as well. I should have it somewhere here. Yes, it will be in Centergy 5213, which is my office. It's then Tech Square. It's Then there's going to be a Zoom link as well. So for the video section, the Zoom link is probably the best idea for you to just join in and ask any questions. Again, the TAs, I'm going to upload it by the end of this week. So hopefully by Saturday or Sunday, this entire page is going to be complete. We are going to have two TAs. It's just a question of who they are at this point in time. Apart from that, in the files, I'll start uploading all the lecture slides. I believe most of it is out. So in the handouts, for instance, there's quite a few things from lecture one that can be very helpful. For instance, anything with respect to linear algebra or any kind of a cheat sheet for linear algebra or probability is there. So if anyone, you need to have a quick guide regarding some of the mathematical concepts that we'll talk about, then these are the handouts that you would want to look at. Same thing with if I go back to lectures in the lectures folder. I uploaded the classification one today. Apparently, the first one has not yet been uploaded. I thought it was, but apparently not. So I'll upload that lecture one as well. But lecture two is what we'll be doing today. I will upload it like a couple of hours, hopefully before the lecture itself, so you can take a look at what that is. From next week onwards, I'll probably use an iPad in order to do some annotations as well. So once I have an annotated PDF, I'll upload that as well into the same folder. What else? So yes, so if I go back to homepage, if you go to the content page over here, yes, the course content, the syllabus essentially has a syllabus that we went through last week. If there's any updated version, I'll keep updating it on this particular page. The course content will have the handouts that I just mentioned. So for the first reading references, there was quite a bit regarding the first lecture. Most of it was more logistical, and it went, we discussed about how we need to use Python, Colab, and there are a number of tutorials that exist for this. Dr. Ahmed, who I think back in 2021, has created a nice tutorial as to using Colab. So that video also, you have it here on the left-hand side. So you should be able to see that. Let me know if any of these links not working, and I'll try to update it as much as possible. So in the reading thing, this is one of the books I'd mentioned, deep learning book. Again, there's no complete textbook that is going to cover everything that we're going to talk about. But if there's one thing that if you're very interested and you want to read, this is probably the best book. So it's completely available online. And all of these things, you'll see a number of these things we'll cover in the course as well. So this particular book is very specific to deep learning, but some of the concepts are more general. So many of the things that we talked about last time and that we're going to talk about today are present in this particular textbook as well. So this can be a very nice resource if you want to go above and beyond what we'll talk about in class. Don't think there was anything other logistical thing. For the video section, the only difference is going to be that you'll have a media gallery on the left-hand side, and the videos are going to be directly uploaded. I believe the lecture one is already online. Lecture two will go online probably by tonight or something like that, whenever Zoom completes its Zoom and Canvas complete their integration together. So be on the lookout for that there. Are there any questions regarding the logistics? Yes. For now, there's no, we don't have that integration yet. but maybe somewhere down the line, I'll see if it's possible. But I realized that the first two lectures, some of you were not there in the first this thing, and maybe some of you are not going to be there today as well, because I think until Friday, you can still have access. You can still, go and change your course schedule. So first two lectures, I'll try to upload it this one. But after that, I need to manually do it. I'll see if it's possible to integrate it. Any other questions? Right. If not, then we can start with today's lecture. So a lot of what we'll talk about today is about a very, very basic task that we attempt in machine learning, which is the concept of classification. So regarding the agenda of what we'll be doing today, it's going to be finishing up a few slides from lecture one that we were not able to do last time, as well as giving an introduction into classification and what it is and how we can achieve classification. Regarding lecture one, we just went through the canvas and logistics part. But after that, we want to talk about the learning algorithm. Like, what is the definition of learning before we jump into more theoretical aspects of classification and practical real life applications of classification as well. And we'll discuss two specific classifiers today, which is the nearest neighbor classifier and a naive Bayes classifier, both of which are have historically been very important and are used in many real life settings, including like financial forecasting and stuff like that. So the second part will be about classification in general, while the first part we'll discuss from a more broad understanding of machine learning in general. So this is a definition we saw last time, which is the definition of a learning algorithm as itself. So a machine learning algorithm is an algorithm that is able to learn from data. And one way to think about it is to try to differentiate it against what we had before, which is that we would create these kind of, it would not have to learn from data, but rather we learn from data, create these kind of automated frameworks, and then allow the algorithm to use that. For instance, hopefully many of you have heard of Fourier series and Fourier transform. So all of these are like classical signal processing approaches. And what they did before was that you looked at a signal and you took these and you realized that a bunch of sinusoids could combine together and analyze and understand what a unknown signal is. So we were the people who decided, okay, a sinusoid is a good representation of this data. And we said that having multiple frequencies of the sinusoid, we can combine it and analyze a particular signal. The difference in machine learning algorithm is that algorithm has to analyze and say that sinusoid is important. And maybe it's a sinusoid is not important. And that's what it usually says, that existing simple orthogonal basis vectors are not sufficient to understand or analyze these signals. And then we have to create these kind of functions, essentially, that is learned from data in order to create an algorithm that is able to either classify, do regression, or any other task, essentially. So the onus is on the algorithm in order to come up with these set of functions that will help us analyze data and predict and forecast and so on. So essentially, a computer program is set to learn from some experience E with respect to class of tasks T and performance measure P. So we'll go through each of these terminologies in the next few slides because it's very important to try to understand what they represent. Again, this particular sentence is adapted from the deep learning book, which we just saw. And we'll go through what they are in a bit. So let's start with the task itself. So what is a machine learning algorithm and what is it supposed to do? So machine learning enables us to tackle tasks that are too difficult with fixed programming. What does that mean? So we have talked about how human beings usually go in and write these if-else statements, these for loops, these programs in order to solve a task. Sometimes the task is so hard, so complex that it's not possible, that we don't know how to solve a particular task. And if we don't know, then that means that we cannot write these if-else programs. In such cases, that is when we'll start thinking about, okay, if we have millions of data points, maybe there are certain patterns within this data. Is it possible to extract these patterns from data and create this kind of a program, which is essentially your machine learning program or your machine learning methodology or algorithm? So an example basically is a collection of features that have been quantitatively measured. So last lecture, we saw this recommendation system algorithm, not an algorithm, but an example essentially, where we had 4 people who had looked at 5 movies and given ratings for those movies. Now, if I were to give a sixth movie and say, what would this person have rated this movie? That is a machine learning task. That is something that we need to solve for, right? So the features in that case are going to be the genre of the movies. It could be a comedy, sci-fi, and so on. So based on how a particular person likes a genre, we can use that information in order to predict what this person would say for another movie. Essentially, that is what features are. So for this particular lecture, we'll discuss more about the definition of features. But since we are giving an overall perspective of what task is, so features is essentially in here in this particular slide. So we can take those features and put it into this kind of a vector. And this is where the idea of linear algebra, matrices, and vectors comes in. You have to be very comfortable with trying to understand these mathematical concepts so that we'll be able to use them in the machine learning course as well. So let's talk a little bit more about the idea of what features are. In images, for instance, case studies, if we just take an image is a 256 cross 256, let's say it's a photograph, or these days 1080 cross 2048, or any kind of a photograph that you have. Each pixel can be a feature. Again, this is just a simple example of what a feature can be. But in an image, each pixel can be a feature. The same thing in the recommendation example, each element within that matrix of the people and the movie is a feature, is something that we can use in order to make a certain recommendation. So essentially, anything that will help us in order to solve a task is something that we're going to be calling a feature. In this case, it's pixels. Last time it was the recommendation, and we'll see a few more things in this lecture itself, which could be considered as features. But any task needs to have features, or maybe a better one thing to say is any task will have features that we are going to use in order to solve it. Any questions about just the basic setup, what we had just discussed? If not, then we'll start with a few common tasks that we'll be doing. The first one of which is going to be regression. After that is going to be classification. The idea of regression is very simple. Given certain features, we want to create this kind of a continuous function that is going to cover all these features. So look at these points that exist within this graph. This is a very simple two-dimensional graph where each point is, you can think of it as either data, or better yet, as some feature that we have currently. So given all these points, we can just plot them. And the goal of a regression algorithm is to come up with this kind of a mathematical program, a mathematical function, sorry, that will encompass all the data points with as a minimum error as possible. Right, so there can be different ways of creating this regression algorithm. A bad regression algorithm would probably connect every single data point. So if you can see my screen here, basically these 2 points will be connected to this point here, connected to the next point here. So it's going to be this zigzag line that connects every single data point, which is a very bad regression algorithm. But still, it is a regression algorithm because it's encompassing all the data points that exist. A better algorithm is something like this, where you see that there is some stationary process, there is some data generating process that is giving you these features, that is giving you this data, but it's a bit noisy. So this is basically a linear algorithm, like a linear y equals mx plus c function. This particular function has y equals mx plus c plus some epsilon noise in it. So that's why, because of the epsilon noise, your points, instead of being on a straight line, are essentially scattered throughout this two-dimensional block over here. The goal, the task in machine learning, is to find that y equals mx plus c without considering the fact that there would have been a noise that is present. Question? Uh, that's a very good question, and that actually depends on the task that you are doing. If we come to rule-based AI, we know everything about the features from beforehand. If we come to machine learning, then we need to define those set of features. If we come to deep learning, the algorithm itself will define those features for us. So in this particular case, at least the first 1/3 of the course, we'll be discussing like general machine learning strategies, in which case we have to come up with these features. And that is very much dependent on the methodology that you will be using. For instance, in that recommendation setup setting, where you have movies, 5 movies and 4 people, we can look at it as genres. That is one feature. Another thing would be to go back to IMDb and look at the actual numbers that are there, the ratings from people. That is another feature that we can use. So the choice of features is something that is in our hands, and we want to make sure that given any task, this is something that we have to choose properly. There's no optimal set of features that is going to give us results, at least at this point. We'll discuss later on how extracting features is itself another learning algorithm. So we'll allow the computer to do it for us instead of us defining it. Always better to have more features. Nothing in machine learning is like can make a definite statement, but for now, yes, let's think of it as all more features is going to be better. But later on, we'll do something called dimensionality reduction, where we'll say that when the dimensions of your features are very high, it is not good. That your computer program, your hardware maybe is insufficient to analyze all that, so you want to decrease the features. But for now, I think it's easier to start with by saying that yes, more features are better for us. All right, so that was regression. Classification is a bit more straightforward to understand. Given n number of data points, let's say they are belonging to a certain class. In this case, let's just say that there are two processes, one of which is red, the other one is blue, and all of them are generating your data. The goal is to differentiate between red and blue in this particular case. And it's very simple, right? So if you look at this, my goal is to create this boundary which differentiates or separate the red and blue points. So just this is classification. This task of separating data points based on some decision boundary that we are going to define is called classification. And this decision boundary here is the classifier. This black boundary that you see over here is the classifier, and all the points are separated because of this classifier. So there are other more common tasks as well. Transcription, translation, anomaly detection. Transcription essentially is this idea that you observe some data point and extract the information from them. So we don't have a task in mind. We don't want to use this information, this extracted information, to either classify or to do regression, but it's just that we want that information out of it. Some kind of textual retrieval form. For instance, if you have ChatGPT, you give it a certain image and you ask it, tell me what is going on in the image, and it gives you a description. That essentially is transcription. That task is transcription. Translation is the input, some sequence of symbols in one language. You want to get the same symbols in another language. Again, very simple. If you think of it in languages, you go to a different country, you don't know the language in that country, then you can use your phone in order to translate the menus in a restaurant or something like that. It's pretty straightforward. But again, this is another task that machine learning is able to solve. Anomaly detection is probably more important from a more healthcare setting. So for instance, if you have heartbeats, if you're monitoring your heartbeats, your watch, for instance, is going to monitor your heartbeats. So there's this specific sequence, the way your heart needs to beat. So even if there's a small deviation from the norm, that means that there is some problem that is happening, some heart-related issues. And the detection of these small anomalies, these small changes to your heartbeats, is essentially what we would call anomaly detection. Again, that was an example of anomaly detection. There's many other kinds of ways we can understand what anomaly detection is, but these are all tasks that a machine learning algorithm is can do and is supposed to do based on the person that is using them. So this is the task part of the machine learning setting that we discussed in the first slide. Next one is a very important thing is the performance measure. Performance measure is, okay, now we have, so let's take that classification example, for instance. We have these nicely separated red and blue dots. Now we want to see if we have the decision boundary that we have, is it a good decision boundary or not? So what we do is we look at the red region and see if there's any blue data points there. And we do the same thing otherwise as well. We look at the blue region and see if there are red data points over there. And based on the fact that if they exist or not exist, we can construct some kind of a evaluation or a performance metric. Now, this example actually was very straightforward. This is probably the best decision boundary that could exist at this point, right? So your performance was top notch. You would have would have gotten like 100% result. Let's go back to the regression thing. Maybe this is not exactly accurate. Maybe there was a slight deviation. Like if you see my cursor, essentially, I'm trying to put another line over here that has a slightly different M and C. Maybe that would have been a better one. And how would you say that is better? Well, one way is to look at where the blue dots are, measure the distance, the 90-degree, the orthogonal distance to the regression line, and say that, okay, this point was 5 centimeters away, the next point was 4. And you kind of add up all these distances against the regression algorithm and say, this is the error for this particular regression model. And maybe there's another model, another like y equals mx plus c, that gives you a lesser error, lesser distance. And you can say that that would be better than this existing one. The goal, the idea of doing something like that is what we would call performance measure. Now I just use distance and error because that is what we're going to use in nearest neighbors, but there can be n number of different ways of trying to create performance measure. For instance, error, accuracy, goodness of fit, cluster purity. There are many ways that you can measure the performance of a machine learning algorithm, and they'll become very important because we'll use them within an automatic framework later on down the line. The last one is this idea of experience. Experience is essentially this idea that we have access to a large training data. And based on that training data, a machine learning algorithm can learn something, right? We require that training data that, as I mentioned before, if we in a recommendation system algorithm, if you just have 4 people and 5 movies, you just have this simple matrix that maybe is not as good for creating your algorithm. But what if you take IMDb data? What if there are like millions of people who have watched millions of movies and you have this extensively large matrix of data, essentially, right? So your experience for your machine learning algorithm is going to be much, much higher and better. Any algorithm that you design on IMDb data is much, much better than the matrix that we saw in lecture 1, which is just a 4x5 matrix. So having access to this huge training data, this experience is very important from a machine learning setting. So let's look at this image here on the right-hand side. I hope all of it's visible to most people. Let me see if there's a light thing here. Finally, there is no light setting here on the table here, but I don't know if it's visible. Let me just look through. So the first column is essentially data points. There's about 150 rows across 5 columns in this sheet. So 150 rows means that there are 150 data points, 150 different flowers in this data set. And they are divided into, I think they have some features, these flowers, which is the sepal length, the sepal width, the petal length, and the petal width. So these are the 4 features that exist within this data set for flowers. And we have the name of flowers as well. There's Setosa, Virginica. There's 2 more names of flowers in this particular data set. It's a very common data set called Fisher's iris data set. It's probably the simplest tabular data that you will ever see. And it's probably the best way to familiarize yourself with machine learning and this kind of tabular data in general, because there's just 150 data points. There's 4 features, which is the length, width of the sepals and the petals, and the name of the flowers themselves, which is the class of the flowers. So in this particular setting, I would say my experience is about like 150 data. I would say the task could be something like classifying which flower it is. Now, I'm not sure how many of you are like flower enthusiasts, but based on just looking the width and the length of sepals and petals, I don't know if you'll be able to classify it just by looking at one data point. But maybe if you had access to these 150 data points, you should be able to create this kind of a learning algorithm that analyzes the features and gives you an output. Based on how we'll use this data, there's actually two types of machine learning algorithms that is possible. The first one is unsupervised, and the next one is supervised learning. So let's take the first one, which is the unsupervised learning algorithms. So in this case, a data set can contain many features. So in the previous case, we saw that there was 4 features, right? So we had the sepal and petals, the length and width, the feature, those things. So a data set can have many features, but what it does not have is the labels. So if you don't have the flower labels associated with the data set, then that means that the only thing you can do is to analyze the features of the data, which would make it an unsupervised learning algorithm. Right, so you can never say that based on these features, this image belongs, this flower is X class, or the name of this flower is so and so. But you can make some very useful properties regarding the flower. You can understand or analyze certain useful properties about the flowers themselves. You can say that given that the petal width is X, X plus 5 it will be the sepal width. Or you can make these kind of generalizations and arguments because you have access to a large data set of points and the features associated with them. Another thing that you can do is creating this kind of a histogram where by observing several instances, we might be able to estimate some random probability distribution. And I'm explaining this from the perspective of Iris dataset, but all the new generative algorithms that have come out, ChatGPT is one, DALI is another one. All of them are essentially these kind of unsupervised generative algorithms where you're not trying to classify something, but you're just trying to come up with some statistics about that data point, which is essentially what ChatGPT does. It takes the prompt that you're giving it and it looks at the knowledge it already has and comes up with this kind of a P of X probability, saying that the next word that I need to spit out has to be this word. The highest probability has to be this particular word, and so on. So it's like a sequence of these generators, these probability P of X generators that are just put one on top of the other, and you finally get a particular sentence, right? So everything, it just comes up from this idea that you can generate a probability distribution, not based on any task, not based on any output that you want, but a very simple a latent probability distribution that you can get. Yes. Yeah, that's it. I wouldn't say the word classify in this case. That would be like clustering. I would use the word clustering and regression in this particular case. So you can get that if you plot the sepal length and width, you can get a nice line or some kind of a parabolic function that will encompass all these points. So the next one is supervised learning algorithm. So supervised learning algorithm, again, it's nice to kind of compare and contrast against what we learned, which in this case is going to be that you have access to the class labels. So each example is associated with a label or a target. So in the Iris dataset, the plant or the flower name itself is, you'll get it. The difference here, more from a mathematical perspective, is from before you had this idea of P of X, which is just a probability of the data point. In this case, there is conditional probability, P of Y given X. So this is something that you can learn in this particular case. Before, you could just learn one generative model of the features themselves, the probability of the features. But now, given certain features, I can tell you what class is it. So given that my petals have a width of 5 centimeter and a length of 2 centimeter or something like that, I can tell you that this belongs to the flower class of, I think Setosa was one of them. So I can make that, not that, I can make that assertion based on knowing the data that exists. And whenever I'm making those kind of assertions, the algorithm that I'll be using is a supervised learning algorithm. And the way the course will be structured, we will discuss these kind of supervised learning algorithms specifically for classification. And then in the later half of the course, we'll discuss more unsupervised algorithms. So with that, I think this is ideally what I should have finished last on Monday, but obviously it was not possible. So now we'll move on to classification, which is just a just one very important task within the machine learning module. So what is classification? I think the previous one was very simple way of describing between the red and blue points, but let's have a more formal definition. So it's a task of approximating of some function f from input variables x to some discrete value y. And this here, the discrete output value variable is very important, that word, because in classification, our outputs are not going to be like this kind of like a essay, paragraph essay about certain image, or it's not going to be like some caption for this. It's just going to be a very simple say output saying that these images here are that of airplanes. Pretty sure you won't be able to see it. This is a very famous data set called CIFAR 10. I've put the entire data set over here, not the entire, at least all the 10 classes that are there in that data set here. I don't think you'll be able to see the exact images on the screen here, but all of the images on the first row are airplanes, the second one are automobiles, and so on. The bottom portion here is a nice way of describing classification. We have given three images here. One, you could clearly see that it's a cat, a horse, and a car. We're going to name them as X1, X2, X3. This is the general terminology that we'll be using for classification, these labels. And then our goal is to get the outputs. The question that we'll be asking is, which category does this image belong to? The first one is a cat, second one's a horse, and the third one is a car. And that is what we want as our outputs. So Y are our discrete labels, our outputs, while X is our set of inputs. Now, we can think of inputs in different ways. Either they can be features, they can be simple data points, and so on. It depends on what kind of machine learning algorithm you're using. If it's accepting the entire image, then that means that the features that you're using is a pixel. If it wants you to do something else, like let's say it wants all background subtraction, or it only wants grayscale images. Your algorithm only wants grayscale images. In that case, you would have to pre-process your pixels and create a new feature set that you would have to give the algorithm F over here. And F is our most important part for the course, which is the machine learning algorithm in this case. So classification is probably one of the most used tasks. You can use it for multiple cases, like email, for instance, spam detection, which whenever you get an email, there is an automated algorithm in your mailbox that has to make this kind of a decision. Is it a good email? Is it something that is suspicious? Is it spam? So all these things it has to classify and then put it into the right box. Same thing with these kind of texture analysis, shape analysis for face recognition as well. If you're using your some phone in order to recognize a face, then it has to create these kind of inputs. It has to create this kind of a shape. It has to measure against the shape that already exists within the phone, the template that you would have given it when you first unlocked your phone. And then it has to say, okay, this is the correct face recognition. I'm going to allow this person in to see all the data inside as well. There are other ways, other examples of classification, including drug design, which currently is a large problem in terms of trying to create these kind of drugs in order to create these kind of medicines for any and all diseases that exist. And other things, literature and art, journalism, education, any kind of text that you get, you should be able to analyze it and say that it belongs to this category. So classification has a number of applications in real life, and is probably the easiest introduction into machine learning. How is classification different from regression and clustering? So these are three very large bodies of machine learning. So we discussed this a little bit before. Classification, all you do is get these kind of boundaries between data. In regression, you model the data. Instead of just saying that this data belongs to this class, you say that this is the generative P of X process that is going to lead to this particular class. Clustering is you have these kind of data points. The goal is to create a representation space where each class is in a different part of that representation space. In other words, if I have a simple image, for instance, if I take all the pixels as my features, and since it's a 2D thing, right? So it's X and Y, and there's an intensity involved with it. I can just plot it. But when I plot it, it's not going to be as good because everything is going to be jumbled up. But maybe if I convert it into a different representation space, like LAB, where it's like a color dependent representation space, what you'll notice is certain objects will be in different parts of that representation space when I plot it. So essentially what I've done is I've created this kind of a transformation algorithm, this F algorithm, that takes a very jumbled up set of data points and puts it in different parts where each of those part is going to represent a certain object or a certain color. And that can be very important based on for certain applications. We'll discuss clustering sometime in February, I think, and regression hopefully by the end of January, but maybe it is going to be February, the first 2 weeks of February. But all these things are very important from a machine learning perspective and something that we're going to be taking a look at down the line. Classification, of course, will be right now. So some terminologies, we have already gone through these terminologies quite a bit. Samples is your training data. This is the iris data set. The rows were the samples. Features is essentially some kind of attributes, measurements, or dimensions about my data. In this case, we had 4 features. Feature vector is I can take each of these things and convert it into a vector. So and somewhere in one of the slides, we had feature 1, comma feature 2, comma feature 3, and you had a transpose in the vector, right? So that is essentially, we can take a data point and represent it as a feature vector. In other words, I don't need this 1 over here. Instead of having this 1, the data point 1, I can just have it as 5.1, comma 3.5, comma 1.4, and 0.2, because that will be descriptive of this particular row, which is going to be 1. So feature vector is the same as a sample. Feature extraction, in this case, we're not actually doing any kind of feature extraction because we are kind of given features. But you can think of feature extraction in this case as some flower enthusiast who went in with a ruler and tried to measure the width and the length of these particular flowers. So that, in this case, would be something like a feature extraction. But the idea of feature extraction is going to be very big later on down the line. So when we discuss deep learning algorithms and more common machine learning algorithms, we're going to spend a large amount of time talking about feature extraction itself. Target class will be the last column over here. The Setosa, versicolor, virginica, all these are different flowers that we are going to be analyzing. Then, of course, there's going to be a learning model. This is the F model that we talked about before. Anything that is able to take inputs and give out outputs is going to be a learning algorithm. The training algorithm is the way we will be training it. So we'll discuss 2 things today, which is going to be nearest neighbor classifier and naive Bayes classifiers. Those are the 2 training algorithms that we will discuss today. And again, there's like many training algorithms that can exist. The last one is the training or evaluation set. Now, this is very important. We'll cover this a little bit more in the next 2 classes, but essentially, given these kind of 160 data points, you need to use a certain number of data points in order to learn, but then you want to see that the thing that you have learned is working, right? You need to have this kind of a performance measure. And to do that, you need to have this kind of an evaluation set. So in other words, among the 150 data points rows I have, what I'll do is I'll take 100 data points for learning, and then I'll take 50 data points for testing. That means that across the first 100 data points, let's say, I'll create this F algorithm. And based on the learned algorithm, I'll take the remaining 50 data points, pass it through them, and see what output it's giving me. And if it's correct 100% of the time, then I can create this kind of a performance measure to say that I have the best possible classifier that can exist in the world because I'm getting 100% accuracy. But more often than not, you're not going to do that. You can't get it, and you'll get something below. And you will say that, oh, I have 90% accuracy. And your friend will come along and say, hey, I did better. I got 91% accuracy. And if, all research papers are basically written this way, one person gets something a little bit more than the other, and they write the paper talking about how they did it. But in order to enable that, you need to have a training and evaluation set that is completely different from each other, that are independent from each other. We'll talk a little bit more about this while actually in the next couple of lectures, and also it'll be a very important part of your homework as well. Oops. I think I went through all these things. All right. So let's look at the first way of classification. This is not a machine learning based classification. It's something called a rule based classification. This is something that we saw in the on Monday as well, when we were discussing non-machine learning based classifiers and non-machine learning based algorithms. This is a very simple true false if else statement. So this is probably your first programming thing that you ever learned, which is given certain marks, for instance, you want to give a certain grade. So let's say you first have this if else statement that says if your marks is greater than something or less than something, then you give particular grade. If it's less than 60, it's going to be grade F. If it's greater than 60, then you ask, okay, is it less than 70? If yes, it's D. Otherwise, you keep continuing forward. So there's this kind of a decision tree structure, and this is what it's called, a decision tree algorithm, where you have this kind of an if else rule based statement to say that one is higher than the other. Hence, this is the grade that is going to be allotted in this case. So it's a very simple way of thinking about a learning algorithm, which in this case also is going to be the same thing. The difference here, of course, is that you don't need this kind of a large data. There's no experience involved here. Somebody has made this decision. Somebody has said that if it's less than 60, it's going to be F. If it's less than 70, it's going to be D. Now, you can probably say that the instructor who has actually made this kind of decision has done a lot of work beforehand, has taught a lot of courses beforehand, and has seen that this is the general setup, general way of doing something. But this is not something that is learned by the machine itself. It's some knowledge that has come prior to the framework. Hence, you wouldn't classify this as like a machine learning model by itself, but rather as a rule-based classification system. The difference between the predictive modeling and what we just had was this here. So training data, you have a huge amount of training data. You will either the network itself or the model itself will extract these features, or you give the features and you learn this predictive model. This is very important. In the previous case, there was no learning of predictive model involved because there was a rules that said that if it's greater than this, less than this, so on and so forth. But in this case, in machine learning, we have a predictive model that we have to learn. And once you have that predictive model, you can then use it on any new data. The first part here is something that we'll be calling a training phase. So you have a model that has not seen anything before this particular point. You want to train that model. You want to make sure that that model has learned something. So that phase in a machine learning algorithm's life cycle is called the training phase. Next comes the testing phase, where you'll have access to new data. So I can give you a completely different petal width and length that a network that the model has not seen before. And based on that, you will still be able to make some kind of prediction, even though it has not seen before, because it has learned something about all these data points beforehand. So that's the difference between training phase and testing phase. Again, you'll have about 100 data points in the training phase and about 50 data points in the testing phase in order to make sure that your model is actually working correctly on the new data. So there's different types of classifiers, case-based, model-based, feature-based, end-to-end, and based on the number of outputs and the number of inputs it is taking. Case-based is essentially, learners don't do anything. So basically, we'll talk about more about this today, which is the k nearest neighbors and case-based reasoning. So the model is not learning anything. It's just creating these kind of functions in order to analyze the data and giving you some results. This is opposed to this kind of model-based reasoning, where learners actually construct models in order to make certain decisions. It's easy to kind of differentiate these two based on the availability of features, but that's not the case. And we'll discuss more about it when I talk about like k nearest neighbors. But model-based is something like you can think of it as all deep learning algorithms that exist are these model-based algorithms, where it's extracting the features, it's analyzing those features and making a decision for you. Feature-based and end-to-end. Feature-based is essentially the model starts by taking some features. I need to give the model some features. I need to tell the model that, okay, in the recommendation system setting, the genres are an important feature for making classification about the movies. It takes in the features as the inputs, while end-to-end, is you don't need to give it any features. It's going to extract features by itself. That might seem very tough right now, but at the present, so all deep learning models that exist are end to end. And anything that you're doing right now, just think of how you would use your phone, right? If you want to recognize an object on Google Lens, you just take out the app, you'll take a photograph of a particular object, and then you'll get the output as, okay, this is the object that you're currently looking at. You're not extracting features. You're not saying that this may belong to this category, this may not belong, so on. Rather, you're just giving it a data point and expecting an output. That is what you would call end-to-end modeling here. So there's no processing that is required. But of course, the learning process typically takes longer than feature-based. That is, Google in their internal servers have spent billions of dollars in order to develop these models that are able to do this, and they've done it across a huge amount of time. But still, as a user, it's much easier for us to use these kind of end-to-end models than it is to use feature-based models. The last one is the type of outputs that we are getting. The first one, for instance, is a binary classification. So very simply put, binary classifiers distinguish between two classes, whether something belongs to a particular class or not. So take this, for instance. Given these kind of, we saw this data set on Monday, which is the MNIST handwritten digit data set. So given all these numbers, my program F is only asking one question. Is this image that of 3 or not? If yes, then that means you'll go to the top arm. If no, then you go to the bottom arm. Essentially, what you're doing here is a binary classification. It's a yes or no question that you're trying to answer. Same thing with the second one here as well. You're asking whether something is a digit or a letter. If the top arm is basically for a digit, the bottom arm is for a letter. So essentially, this is a very simple classifier that is based on the kind of output that you're looking for. If you're just looking for a yes or no question, then the kind of classifier that you're using is going to be called a binary classifier. Some very important classifiers like support vector machines, SVMs, and linear classifiers are part of these binary classification. Now, you might think that this is not very important, you're just doing between two classes, but you can think of this as a subcase of multi-class classification, and you'll be able to use this. So SVMs are probably one of the most important binary classifiers or linear classifiers that exist. We'll discuss about them sometime in February as well, of course. But right now, you can just think of them as these linear classifiers that just appended one on top of the other. So they make one binary classification, then they make another binary classification, and then they make a third binary classification until you can get n number of classifications that are possible. And that basically is this kind of multi-class classification. So in this particular case, given all these numbers over here, the goal is to ask what number is this? So this is a 3, this is a 9. I believe the third one here is probably a 5. The next one is a 5 and 0, 8, and so on, right? So all these numbers have to be classified. A machine learning algorithm has to take all these numbers and give it a certain label. You can do it in different ways. The simplest way to do it is by looking at 3 here. You first have a binary classification for 0. You ask, is it a 0 or is it a 1? If it's not is it a 0 or is it not a 0? If it's not a 0, move on to the next binary classifier. Is it a 1? Is it not a 1? Is it a 2? Is it not a 2? Is it a 3? Is it not a 3? And as soon as you come to 3 and you say yes, then that means you have classified it, right? So you can take a number of binary classifiers, appended one on top of the other, and you will be able to get this kind of a full classifier for n number of classes in this particular case. I think this is MNIST dataset again, so it's about 10 classes that exist. But this is one way of thinking about what a multi-class classification or a multinomial classification is. Now, multi-label classification is slightly different from a multi-class classification. In the multi-class classification, given a certain image, there was one class associated with it. In this case, there can be multiple classes, right? Given this image, you're asking the question, what objects are present in the image? There's a house and there's a tree. So that has to be yes for 2 of these classes, house and a tree, while there's clouds as well. So there's going to be yes here, while beach, mountain, and animal are going to be no's. So the difference between multi-label and multi-class is hopefully clear. Multi-class is each image can have a single class, but there are multiple classes available, while multi-label is that each image can have multiple classes, and the goal of the algorithm has to be to predict if each of these classes is available or not. Same thing with multi output as well. So instead of just saying yes or no, you give this kind of a likelihood value. Think of it as a probability for now. You can say that a house, there's 92% chance of a house being in this particular image. There's 89% chance of like a tree being in this image. So instead of yes or no, simple classification, you start thinking about it from a probability perspective. There's a very good chance that a house exists. There's a very good chance that a tree exists in this setting, and so on. So in this course, again, there's like a very, very large number of classification algorithms that exist. We'll be looking about 6 of these algorithms in this particular course. We'll start with nearest neighbors decision trees. We already talked about it quite a bit, which is a rule-based algorithm. But we will have a few slides on decision trees as well. We'll start with nearest neighbors and then move on to naive Bayes. My original idea is to finish these 2 today, but let's see how much of that is going to be possible. So let's start with the nearest neighbors algorithm. We'll discuss mainly, okay, let's start with just an overview of what the nearest neighbors algorithm is going to be. Let's say I have this loan scenario. So I have about 11, so I'm a bank where about 11 people beforehand have come to me asking for loans. So I have this in this form of a table over here. So the first column is the people who have come in. 1 refers to the first person, 2 refers to the second person, and so on. I have a few features regarding this each person. I know the age of the person who has come in. So the first person who came in asking for a 40,000 loan was a 25-year-old. And then there was someone who came in who was 35-year-old and who asked for a 60,000 loan, and so on. I have a number of these data points. And the right side is probably what you would call as a label. Sometimes what is a label and what is not a label is very arbitrary. It's basically what I am interested in. As a bank, I'm not really interested in classifying the age of the person who comes in. What I want to know is if they'll pay me back the loan or not, if they'll default on their loan payments or not. If no, then that's good. They're giving me back the thing. If they do default on their payments, then that means that's bad. That means I should not give them the loans. At least that's the goal of the machine learning algorithm. Now, how do we basically create this learning algorithm? The first one would be this kind of a nearest neighbor algorithm. I'll talk about K in a little bit, but nearest neighbor algorithm, very simply put, I'll take the features that exist. So in this case, there are 2 features, right? There's age, there's loan. The default again is a label, is a target or a label. I'll take age, loan, and I'll just put it into this kind of graph here. So default red is basically the person has defaulted. Non-default is no, which is the diamond blue over here. So so let's take the first one here. This is 20, and the person has asked for like a 25,000 loan or something like that. Right. So let me try to find this. Okay, 20 with 20,000 loan. So number 4 here is the blue dot, the left and the bottommost blue dot. So all I've done is taken the parts of this table and plotted it within this graph over here. That's it. I've done it against all 11 things. Now, what nearest neighbor algorithm does is that given this kind of a new sample that comes in, so let's say I have a 12th point right now. So this is all training data. So new data during the testing phase, what happens is the 12th person comes in and asks me for a loan. I know that this person is going to be about like 48 years old, or I ask him what his age is, if it's 48 years old. And if this person is asking for about like $145,000 loan, I can now plot this person's features within the graph I already have right now. The goal is nearest neighbors is basically to calculate the distance. It's a very simple way of saying that if all the people around you have defaulted paying their loan payments, you will also probably default on your loan payments that you won't pay as well. Of course, again, the age and loan is a very bad set of features. This is just for an example purpose. This is just saying that given these kind of features, if the distance from all the adjoining all the people in my training data were doing a certain thing, which is defaulting, then maybe you're going to default as well. So it's a very simple way of thinking about this kind of a thing. So a very important part here is the definition of K and the definition of distance. So K is basically the things, the number of people that we are looking at, right? So I think that's there in the next slide after that. But let's talk about distance actually, apparently first. So this distance is very important as well, because how do you calculate the distance between this unknown sample and a set of training data, right? So the simplest thing is what we always think of is the first one here, which is the Euclidean distance. Now, Euclidean distance is good when there are no anomalies. If I go back to this particular point here, let's say this red point was here. Instead of it being here, if it was somewhere over here, if a 48-year-old person had asked for a $1 million loan, it's somewhere over here. If you use Euclidean distance, what is going to happen is that it is going to disproportionately affect, this one point will disproportionately affect the outcome for this new data. Instead of having 4 points here, all of which are equally weighing how important, or equally weighing whether your person defaults or not defaults, 1 point is going to severely affect whether this person will default or need not default based on your learning algorithm, which is bad. We don't want to do that. We want to have like a balanced outlook at what our output is going to be without being affected by just one person in this particular case. And that's why you might try to use different distances. You might try to use Manhattan distance. You might try to use Minkowski distance, and so on. Again, these are all based on continuous variables. But maybe my features are not continuous. Maybe my features are categorical. In that case, there are again different kinds of distances, Hamming distance, and so on. So the choice of distance that you are going to make is going to affect your nearest neighbor algorithm quite a bit. Again, there's no one good choice. I cannot tell you that this is the best choice that is possible. One thing I haven't put here is Mahalanobis distance. That also is a very good distance measure that is generally used in most algorithms these days, because that takes the shape of the manifold into perspective as well. But there's a number of distances. There's no one good answer. The best way to do it is to try a lot of these things. Or if you have a good idea of what the features are representing, then it's something that you can use. So the next one, the next important part is choosing K. And what is K in general, right? So if I go back to this particular slide here, K is the number of points that I'll be using to analyze. So in this case, my K is 4. So I've taken a new point and I've chosen these K4 points in order to make an analysis. Now I could have chosen 5 as well. Like this point is also pretty close by. So I could have had K equals 5 as well. So that is a hyperparameter. That is something that we call hyperparameter, where it's something that changes with the algorithm. Any person who does this, someone might take a 3, another person might take a 4, the last person might take a 5, and so on. But essentially, K is this hyperparameter where you'll have to go through many of these numbers in order to see which the best algorithm is giving you. Again, the learning strategy is going to be to define what this K is going to be define what this the distance that you're going to be using is, and you're going to use all those things and evaluate it to see what the best performance metric that you are going to get. So in this particular example, let's say age and loan are the two numerical features, and default is your target, which is basically your label. In this case, I'm getting this kind of a new data point over here, which is basically, and I'm using K equals 4, and using probably Euclidean distance for this kind of approach. So here we have so our new case is 48 and 142. I think I mentioned 48, but I probably missed the 142 part. So our new data point, which is the 12th person who's come in, is of 48 years of age and is asking for $142,000 of a loan. The goal for us is now to see if this person is going to default or not. If the person defaults, then that means that we shouldn't give them the loan. If the person does not default, then that means that we should give them the loan. So the best way to do it is by taking the nearest instance. Let's start with a very simple k equals 1, right? So I'm going to take the nearest data point and calculate the distance, 8,000.01. So if k is equal to 3, then the nearest three neighbors are going to be 1159, and the classification is also y. Again, this is based on some measurement that you are going to do based on all three distances rather than just a single distance. And if all three of them are saying yes, yes, and yes, then basically you're going to make this kind of default or not. So in this particular case, maybe the first one was going to be default. The distance that you're going to use from the first one is going to default. So you are going to say that, okay, my green, my new person who's going to come in is also going to default when you're just looking at a single neighbor. But when you take three neighbors, so green, green, blue, blue, and red, then this basically means that you have two people who are going to not default and one person who's going to default. So it's very simple. It's very straightforward. You are going to now say that, okay, this person is not going to default because two neighbors who are nearer to him have not defaulted their loan payments back. This is probably the simplest algorithm that exists. All you have to do is take this kind of a graph and create these good features so that when you take the distance from those features, you have what you'll get what you want essentially in your algorithm. The heavy lifting is being done by you because you are choosing the features, you are choosing the distance algorithm, you are choosing the k value, which is the number of people you are analyzing. But once you have all those things, you can let your algorithm basically get the classification setting at this point. Does this make sense? Yes. Yeah. At that point, you can start taking distances. So instead of saying that this is the nearest distance, I'm taking a no for this. I can say that this is, let's say this is 8,000, while this is 12,000. This is 9,000, and this is 9,000. So 9,000 plus 9,000 is going to be 18,000, while 12,000 plus 8,000 is going to be 20,000. So among these, the blue ones are nearer technically, right? Because it's 18,000. So you can then say that this person is going to non-default based on the fact that the sum of these things are going to be less. But again, that sum is also a distance. That sum is also going to be this kind of a Minkowski Manhattan distance. So you're just adding the values over there. There are different functions that you can take. So I can say that this person, for instance, is very trustworthy because this person has. So the real answer to what you asked is by I need to add more features, which is that I can say that this person is very trustworthy. This person has taken 25 loans before this, and he has paid back every single time. While this other person is not as trustworthy because they've only taken one time or something like that. But if you don't have access to those new feature information, then you have to use these kind of pseudo information, which is just add up the distances and see, okay, this is greater than the other and so on. Yeah. All right. So another important part that we need to take care of is this idea of data normalization. Sometimes what happens is that variables have different measurement scales. For instance, sometimes my loan is in dollars and age is in years, right? So $40,000 is not proportional to 25. Just the number 40,000 is not proportional to 25. 60,000 is not proportional to 35. 20,000 is not proportional to 20. So what happens is that your algorithm, so this number here, for instance, 8,000, if you had just thought that this is part of the age, you would be very confused why this is like 8,000. So in this case, what has happened is that the loan has disproportionately affected this distance. And this is what I was talking about using Euclidean distance, for instance. Your 142,000 minus 150,000, 8,000 whole squared. Right? This is much, much higher. It didn't matter if this was for like 100 minus 1. If a very old person of 100 years versus like a baby of 1 year had come in, there would not have been a change in your algorithm at all. Because this number here is not going to affect the overall distance because the second number is so large that there's a very disproportionate setting between the two things. So what you would have to do in such cases is this idea of data normalization. Instead of taking it as 40,000, 60,000, 80,000, you can use this very simple formula of normalization where you subtract based on the minimum and then divide it by the range of your values. So in this case, what I would do is I would subtract 40,000 by 18,000 and subtract it by 220 minus 18. So about 202,000, 202,000. So it's going to be like 28,000 divided by 202,000 is going to give you all these factors. So I'm taking each column here and normalizing it based on the data that exists. Once you do that, your results will be much better. When I say better, it's basically that each feature will be equally represented in your data set rather than something that is overtly contributing to your results. Any questions about data normalization? This is probably very important. Yes. Mhm. So I'm sorry, you were asking. Okay. Yes. Yes. Categorical, you wouldn't, it depends on what kind of categorical labels you are looking for as well, right? So in this case, one categorical label can be something like, I'm blanking on, so which kind of laptop they're using in order to go for the loan. So it could be like an Apple, it could be like Dell, it could be Asus, like, all these other things. So these are categorical labels essentially, right? So what you would do in that particular case is to use something like a Levenstein distance or whatever, where you're taking the type of laptop you're doing, that you are getting this kind of a loan thing in, and you're subtracting the number of people who have used that particular laptop from before. So there are different ways of doing it. There are different distances that you can use it. So this is based on the Euclidean formula, while that's what I had mentioned here. You can have different distances. You can have different normalization factors for categorical labels as well. Another simple thing is by instead of taking categorical labels as 0 to 10, I would suggest to always take it from -5 to 5, because you put it across like a single mean, which is essentially what you are doing here as well. Instead of taking it from 140 to 150, you're making it between like 0 to 1. For categorical labels, if you make the mean 0 and your standard normalization to be between something -1 to 1 or whatever, it's the same thing. It's just that instead of making between 0 to 10, you're making it between -5 to 5. So 10 square is not going to be as effective as something like 5 square, if that makes sense. Yeah. Oh, no, no, no. So Apple is 0. Apple is 1, let's say. Dell is 1, 2. Asus is 3. And let's say you have 10 companies, right? So you'll have 10 different laptops. So you shouldn't subtract, if you subtract 10 minus 1, it's going to be 100. So if you subtract between -5 and 5, it's going to be much better. So you take 1 and make it -5. You take 2 and make it -4. It's, as simple as that in this particular case. Yes, yes, yes. In this case. That is because the number of people who have used Apple, let's say, is 5, while the number of people who have used Asus is 100. So you have designed it in such a way that these categorical labels are based on the frequency of occurrence. We'll actually talk about this in the next case. So categorical labels, you have to design those labels, not just use the numbers over there. In this case, numerical labels, it's like, you have access to 40,000, but categorical labels is something that you give. And it's something that can be taken. So one example of Apple being 1 is the number of people who have used that particular laptop in order to ask for the loan, versus Asus will be something else. So then you can divine those categories from that feature, basically. Does that make sense? Yeah. Right. Unfortunately, there's like 4 minutes for naive base. I don't know if it's possible for us to do it, but I want to cover just this one idea very quickly, which is the idea of a frequency table. So naive Bayes is essentially the first learning algorithm, like a probability-based learning algorithm that we'll be looking in this course. It's used for both classification and regression, and you'll see why. While our goal will be classification for now, it can be used for regression as well later on down the line. So there's a couple of, actually, I'll talk about the problems with this thing later. But the good thing about naive Bayes is that it requires very small computational power and it works very fast, even on large data sets. So let's very quickly look at an example of what this is. So in this case, again, we need to derive these kind of labels. And one of those labels that we'll be deriving is this kind of categorical labels. So let's start with a very simple example. When you're young, you want to go outside and play, but your parents probably said no or yes sometimes. Now that you're older, you want to look back and think that, okay, why did my parents say whether I should go out to play or not to play? And one thing that you can come up with is maybe you'll say, okay, weather was probably a very major important factor. So you start creating this kind of a table. If it's sunny, then the play was going to be, then your parents would not have allowed you to play, which is going to be a no. If it's overcast, maybe on this was day 1, they would have allowed you. Day 2, it was overcast and you were allowed to play. Day 3, it was rainy, you were allowed to play. Day 4, it was sunny and you were allowed to play, and so on. You have, I think there's like 15 or 16 rows where based on the weather conditions, you were either allowed to play or not allowed to play. This is the data that we start off with. The first thing that we do is convert this data set into a frequency table, also called this kind of a contingency table. So I think I'll stop after we do this particular slide. But essentially what I do is I look at all possibilities here. There's sunny, there's overcast, there's rainy. So there's 3 possibilities. And I just start counting the no's and yes for each of these things. So this here is a frequency table. I can create these kind of labels based on the frequency of occurrence. So if it's sunny, I look at the number of no's that exist and I update the no part of this table. If it's yes for sunny, I'm going to update that particular part over here. So 2, 3, 3, 2, and 0, 4, essentially. This is going to be my frequency table. And based on that, I can create all these probabilities. I'm going to stop at this point because there's no way I'll be able to talk about these probabilities. I would need to go to the next slide as well. But just take a look at this particular set of slides. It's a nice way of trying to understand probability, marginal distributions, and everything. The goal will be to get like P of yes given rainy, and that is something that we want to see at the very end.